Alright, so this is video number 2 in naming and writing the formulas of compounds. When an instructor gives you the periodic table that you're going to be using for this part of the program, commonly he will give you a list of the common ions that go with those elements on the periodic table. There are usually a variety of other ions that you're going to find on that periodic table as well as a list, of course, what are referred to as polyatomic ions. Now there are two types of ions, of course. There are cations, which are of course the positive ions, and the way I always remember that, of course, is by seeing the T in there for positive. So the cations are the positive ions. The anions, I think N is in there, negative ions. Now we'll find some polyatomic ions, which are basically ions in which there is a group of different elements that combine together and stay together, usually during a chemical reaction. And what will happen, of course, is when we're naming them or writing formulas, we have to actually recognize that there are certain rules that have to be followed. So let's have a look, going back over to what we've done previously. Now you recall, of course, that when we're dealing with two elements in a compound, all we have to do is recognize those two elements and, of course, write down the name of the metal, which in this case is potassium. And, of course, the first syllable of the non-metal, in this case oxygen, would be ox, and then we add I-D-E. Alright, and that's fairly straightforward. We've got some practice doing that. Alright, now when we look at the next one, of course, that one's very straightforward too. We've got calcium and we've got phosphorus. That becomes calcium phosphide. So those are pretty straightforward. Alright, now when we look at the next one there, you'll notice that we've got calcium, we've got phosphorus, and we've got oxygen. Now the real problem here, of course, is that we can't go, this is calcium phosphide oxide. That makes really, in scientific terms, no real sense. So you'll recognize that there are three different elements. Alright, and the moment you recognize that there are more than two elements in a compound, what you're going to have to do is go to your list and have a look at the various compounds that are there, the ions that are there, and try to recognize what that group actually is. Well, calcium is calcium, right? But you'll notice that right here, that is the group that we have combined with it, and that's what's called a phosphate. So what we're going to do, of course, is we're going to have a look at it, all right, and we're going to go, well, the metal is still calcium. That hasn't changed. All right, and then, of course, we look at the PO4, and that's phosphate. And oh, look, lo and behold. Now, as a clue, recognize, of course, that the 8 basically tells us that we have an anion or a polyatomic ion that actually contains oxygen in it. So that's a fairly good indicator. Sometimes, of course, if there's one less oxygen than the 8 compound, it'll be referred to as an ite. So if this was, for example, Ca3PO3 2, all right, that would be calcium phosphite, and of course you'd find that right next to it, right there. All right, so that's fairly straightforward. Now, so it comes up fairly easily. All right, it's just simply a matter of recognizing that if there are more than two elements, that there's probably going to be a polyatomic ion, sometimes referred to as a radical, in that compound. And the naming just follows through. Please note that you do not change the last part of that, the 8, into an ide. It stays as the 8. Alright? Now going down, of course, to writing formulas to these, there's a few little tricks that go with that. You remember, of course, when we're writing the formulas for these guys, alright, that we recognize, of course, that we put down the element symbol and the combining capacity. All right, and then oxide, of course, is oxygen. That's O minus 2. And you recall, of course, that we exchange those numbers because the aluminum, what will happen is going to give up 3 electrons, and each oxygen can accept 2. So when we actually do this, of course, the way that those two would combine together is, of course, if we'd have to have 2 aluminums giving up a total of 6 electrons and 3 oxygens accepting a total of 6 electrons. So that's fairly straightforward. Now the same rules, let's remind ourselves of the rules, of course. If the combining capacities were, for example, if this was a 2 and this was a minus 2, then of course they would cancel out because 2 electrons given up, 2 electrons accepted. If they're multiples, of course, a 6 and a 3, for example, then of course we would require that we reduce those by the common multiple. All right. Now, when we're actually talking about compounds that actually have a radical in them, or a polyatomic ion, what's going to happen is that we're going to follow the same rules, but there are some differences. All right, so we're looking at this again. Of course, there's the aluminum. All right, so we go aluminum plus 3. Now, looking at your chart there, you look for nitrate, and you'll see it. It's right there. All right, and it's, oh, look, NO3, and it's got a combining capacity of -1. Oops, sorry about that. Okay, so what we're going to do is we're going to write down that polyatomic ion. All right, and it's got a -1 combining capacity. So here's what's going to happen. Obviously, is the aluminum is going to give up 3 electrons, and each nitrate can only accept 1 electron. So what that effectively means is we're going to need 3 nitrates to accept those 3 electrons. So what we're going to do, and I'm going to show you the wrong way first. All right, so the 1's going to come down to there, and the 3's going to come down to there. All right, and what would happen, of course, is you'd say to yourself, well, we'll just bring the 3 down there. Well, that's definitely not it, because if you could actually make this compound, all right, it wouldn't last very long, because this is producing a massive amount of oxygen. It'd probably blow the whole hole in the side of your wall or something like that. All right, too much oxygen, basically. All right, so what has to happen is when we're actually bringing those numbers down, and the number that we're bringing down is more than 1, what we're going to do is we're going to take our polyatomic ion and put it in brackets, and then we're going to take that 3 there, and we're going to put it on the outside, which makes more sense. So what that basically means is, based on what I talked about right here, all right, I said that for every aluminum giving up 3 electrons, we're going to need, each nitrate is going to be accepting 1 electron. So we need 3 nitrates. That's what that 3 on the outside of the brackets represents. All right, and effectively what it does is it multiplies everything that's inside, which is significantly different. Right, so right now we've got 1 aluminum, we've got 3 nitrogens, and we've got 9 oxygens, which makes a lot more sense. All right, well, let's look at these last 2. All right, let's pull it up a bit more. Here we go. Okay, so let's do the same thing. All right, so iron is Fe. Now, you remember I talked about this previously. We'll get into more detail in another video with respect to this. But if you look at iron on your periodic table, you're going to find, of course, is that iron has 2 different combining capacities. All right, it has a +2 and a +3. This says use the +3. All right, so we go up there like that. Now, phosphate, of course, if you look at your chart here, right, phosphate right here, right, is PO4 -3. So that's what we're going to write down. All right, is PO4 -3. All right, so recalling what we did previously with formulas, all right, you remember that in this case, iron is going to give up 3 electrons, and each phosphate can actually accept 3 electrons. So what's going to happen here is really simple. They're going to combine together, and those 2 combining capacities are going to cancel out. So our formula in the end is simply going to be FePO4. They cancel out. Try to make sure that you're dealing with the combining capacities. Don't fool yourself into thinking that you're able to actually touch that, the subscript that's in the phosphate there, because of course you'll change the formula completely. All right, let's do one more example here. We've got chromium 6 phosphate. So you find chromium in your periodic table, all right, and it's chromium +6, all right, and then the phosphate, of course, is PO4 -3. Now, we did something like this before. Remember what I said? All right, when they are multiples of each other, you're going to divide by the common multiple. Well, the chromium here is going to give up 6 electrons. Each phosphate can accept 3 electrons. So what that basically means is we're going to need 2 phosphates, each accepting 3, to total 6. So yeah, we're going to do the crisscross. All right, that's going to come down to there. That's going to come down to there. All right, and we're going to end up with Cr3 PO4 6. But of course, those are multiples of 3, so we're going to divide by 3 and end up with Cr PO4 2. All right, so it's fairly straightforward. I mean, the same rules still apply, but there are some issues. To do it safely, if you're not too sure if you need to put brackets around a radical or not, put brackets around it all the time if you want. All right, it's not wrong. It's not strictly speaking completely right, but it's not wrong. You won't probably, if your instructor is seeing that you're doing it right, he won't dock you for putting that radical around your radicals, those brackets around those radicals all the time. All right, so hopefully that's clarified a few things, and obviously we'll continue with another video on multivalent metals on the next one. All right, good job. Thanks.